Thank you, everyone. Yeah, so my talk is a bit long, but I try to go over it quickly. So I try to speak fast. Okay. Yeah, so the estimated global wave energy potential is about 1 billion kilowatt. What this means that assuming that an average household consumes about 1 kilowatt of electricity at any time, there is enough electricity for 1 billion homes. The first known patent on wave energy dates back to about 200 years ago, inspired by how waves could move an ocean liner. In the years that followed, wave energy devices used to be called wave motors. Here's one proposal from 1886. It has some sort of pendulum inside, which can rotate about a hinge. And then the relative motion is used to drive a pump. Here's another one consisting of heaving floats attached to a pier. And this one here aims to utilize both waves and tides at the same time. And this one here is supposed to take all degrees of motion into some useful energy. This one is really built. It's not very clear what it is actually. From the description, it seems to be like a plank and then connected to a giant wheel in some ways. And this one here is consisting of 3 floats and take the relative motion between the floats. And the one below use the wave action to compress air into pipes. Interestingly, these two are recent proposals, and they look very much alike, like devised 100 years ago. And this one here is early oscillating water column device. So it works by, so there is a tunnel there. As the wave comes, this water column will rise and fall, and that would drive compressed air, which is used to drive a turbine connected to generator. And this one is an idea, an old idea, so from 1900, of a wave-powered navigation buoy. It was only realized much later in the 60s, and actually there is a Japanese company now that manufactures these buoys. And this one is another different idea, so it's of a much larger scale. The idea is actually based on a conventional hydropower plant, but it runs with seawater. So the water overtops the reef, and then it is collected in a lagoon, and then pumped to a bit higher elevation, and then it will feed a turbine, and before the discharge going back to the sea. And what is interesting here is that in the proposal, this guy Walton Bott, he also proposed to put fish in the lagoon. So is an early example of multi-use of the ocean space. And there are many more ideas. So a 1976 report estimates that over 340 British patents on wave energy were granted between 1856 and 1973. That's not considering patents from other countries. Before the 70s, however, there was no pressing need to look into this alternative source of energy. A comment to an 1892 paper reflects the general sentiment. But then came the oil price shock. This spurred a worldwide search for alternative sources of energy, including wave energy. So in the University of Edinburgh, Professor Stephen Salter experimented with various shapes in a wave flume. And he arrived at a shape looking like a nodding duck. I'm not entirely certain how exactly it is supposed to resemble a duck, but that's probably about right. A full-scale duck would use this up and down bobbing motion to drive a cleverly designed radial pump, hydraulic pump inside it. But what makes the duck different from earlier wave energy devices, or rather, what makes Salter's work different from earlier works, is that he was able to show very convincingly that near complete wave energy absorption is possible. So this is a photograph, like 1 second exposure photograph. This photo is very informative. It says a lot of things about wave energy absorption. So here is a model scale duck under wave action. The waves are coming from the right. The thin line on the left is probably meniscus. We can assume that there are no waves going to the left. We can tell the height of the incoming waves from the average thickness of the band on the right. The small kinks mean that there are small waves going to the right, say about 1/5 of the average thickness of the band. So since wave energy is proportional to the square of the wave height, this means 1/5 square is 1/25. So about 4% of the incoming energy is going to the right. But what goes out to the left is 0 because there is no wave. And that means 96% of the incoming energy is absorbed by the duck. But that's not the whole story of how modern wave energy research began. Let's hear Salter's own account. In September 1973, I caught flu. My wife said to me, with callous indifference to my misery, "Stop lying there looking sorry for yourself. Why don't you solve the energy crisis?" It seemed a good idea at the time. What she wanted was something which would provide the vast amounts needed, which would be clean and safe, would work in the winter in Scotland, and would last forever. It is a good thing for an engineer to have the design objective clearly specified. Okay, so as a response to that, the UK government launched a wave energy program. So a number of devices were being considered. And here are some of the most promising ones: the Salter duck, the oscillating water column, the Vickers device, which is a submerged version of an oscillating water column, the Bristol cylinder, the Lancaster flexible bag. But also in the rest of the world, things are happening. And in contrast to the UK devices, which are about as long as the wavelength, research activities in Norway revolve around devices which are much smaller than the wavelength. They are known as point absorbers. And a remarkable result, which was discovered in the late 70s, is that a point absorber, or in fact a wave energy device in general, can absorb more power than what is incident upon it. This is why we avoid using efficiency when we talk about wave energy devices, because in theory, a wave energy device can be more than 100% efficient. This period also saw the construction of demonstration plants in Norway. One is a tapered channel plant, which uses a tapered channel to squeeze water so it overtops and fills a lagoon. Again, a hydropower plant. And the other is an oscillating water column. It should be mentioned that during this period, activities were also carried out in other countries. And I would say that the 70s to early 80s are probably the most fruitful period in wave energy history. Sadly, with the decline of oil price, urgency faded in the 80s. Funding was cut, and as a result, wave energy research entered a period of inactivity, which lasted for nearly 2 decades. Devices that were so close to being put to sea were abandoned, including the Salter duck and its contemporaries. The situation improved after the turn of the millennium, along with the increasing awareness of the negative consequences of fossil fuels. So nearly every country in the world today has set renewable energy targets and policies. We are yet to see how this would make a difference in the long run, but research into marine renewables is picking up again. Grid and non-grid connected sites have been established around the world. These are open sea facilities where large-scale devices can be tested in real ocean conditions. Here are some of the recent devices. The palamis make use of relative motions between multiple segments. The wave bob is composed of two heaving bodies and makes use of relative vertical motion between the bodies. The wave star consists of a row of floats. The oyster is a bottom hinge flap. The penguin is a floating body with an internal pendulum. The core power is a point absorber tethered to the seabed. And this one here is called the anaconda. It's an interesting concept, unlike the others. It is basically a rubber tube filled with water. So yeah, it's interesting how these people got some animal names for them. Let's now consider some misconceptions about wave energy. First, people often get confused with waves. Basically, wave is a disturbance that moves through a medium. As waves travels, energy is propagated, but the medium only moves locally. This is different from wind, which is a flow of air, or from current, which is a flow of water. One key principle of wave energy absorption is that to absorb a wave, we need to generate a wave with the right phase and amplitude. It is not really true to say that we want the device to move as much as possible. If the motion is too small, we don't absorb anything. Likewise, if the device moves too much, we don't absorb anything. The motion has to be just right. Another common misconception related to this has to do with energy counting. This is easier to understand in wind turbines. If the turbine is absorbing energy, then the wind velocity after it passes the turbine has to decrease. Thus, in theory, it can be shown that the efficiency of a wind turbine cannot be greater than 60%, a result known as the Betz limit, discovered 100 years ago. With wave energy, it is basically similar. If a device is absorbing energy from the waves, then the wave heights after they pass the device have to decrease. Yet we often see illustrations such as this one here, where nothing seems to be happening to the waves, meaning no energy is taken from the waves. It is often said that the wave energy is where wind energy was 50 years ago. I think this is an understatement. It is true that the use of wind to produce electricity took place only last century, and the three-bladed design that we see today became widespread probably only in the last few decades. However, people have successfully used the principle of aerodynamics to harness wind for practical use hundreds of years earlier. So the first windmills were already in use about 1,000 years ago. And designs quite similar to modern wind turbines we see today have been around since the 12th century. So we shouldn't be too surprised if wave energy has not yet converged to a single technology. The first known patent on wave energy was filed only about 200 years ago. Wave energy devices simply have not been around for long. With waves, we are also dealing with an extra variable. Speed in wind is analogous to amplitude or height in wave, but waves also have periods. Wave energy devices need to work well across a range of different wave periods. Is there anything wave energy can learn from wind? Modern wind turbines are much better prepared than present wave energy devices to cope with variability. A modern wind turbine has a range of control handles to cope with the ever-changing wind speed and direction. It can orient the rotor into the wind, it can feather its blades, and is equipped with various brakes to ensure its survival in extremes. Most wave energy devices today do not have these adaptive capabilities. And here are just some examples how we could potentially include adaptive features into a wave energy device to improve its performance and to better cope with extremes. Almost there. So where is the best location to develop wave energy device, and why is this relevant for the Great Southern? Which one would you choose? Say Portugal, with a high mean annual power, or Ecuador, which has much less? This is how the wave power level at the two locations vary over time. Portugal in red, Ecuador in black. a mean value does not say anything about variability. The best locations to develop wave energy technology would also have a low variability. So I think this region here is quite special because it has quite high mean level, but also quite little variability. So this is what is a good place to develop wave energy device. We need to give priority to developing a viable single device. It doesn't have to be big, but it has to be in the water for at least a year and produce at least 30% of its capacity. We still have time, but not much. Going with business as usual scenario. This is the last one, actually. Coal will last for another 100 years, oil and gas each for another 50 years. Thank you.
Thank you.